Hi, I'm Jules. I'm an ID 125 and I'll be teaching you FNDMATH quiz number 3, part 1. But first, let me show you a 120-degree angle. Notice anything wrong? Here, I'll give 2 more angles. These share the same magnitude surely and are geometrically valid, but they are functionally different from one another as they lack 2 parameters: position and orientation. These angles floating in empty space are only defined by their own properties. To make them useful in a larger system like a graph, we need a universal frame of reference. And such, we must lock the angle to a grid. This is called the standard position. This is the bridge that connects the shape of geometry to the equations of algebra, and that is called analytical geometry. But why do we need this exactly? What applications will I encounter that would need this sort of consistency in my engineering journey? With this universal framework, it is possible to relate to you the magic of angles to the engineering disciplines that deal with forces, motion, and orientation. Let's say I have a reference line at the positive x-axis. From this initial side, we measure our angle at 45 degrees, which opens counterclockwise. This simple agreement is what makes trigonometry not only possible, but powerful and applicable. The standard position turns our ratios sine, cosine, and tangent and puts them into the x and y plane, making them usable beyond right triangles, which makes them essential for what's coming next. Now, let's say we have a physics problem, and we want to decompose this vector into 2 parts. With our standard position, we know our angle is 35 degrees coming from that axis, and to figure out our x and y component using the formula given, which is the magnitude times sine or cosine theta, our starting point is consistent. So no matter how many times we measure, if we put the same values of angles and magnitude, we get the same vector outputs from decomposing our initial vector. Okay, let's apply this to a real-world structure, like a bridge. It is subjected to a complex web of forces. There's force of the wind, the constant downward pull of its weight, and the tension of the support cables. To ensure the bridge is stable, engineers must calculate the components of every single one of these forces to make sure they all balance out. This entire analysis depends on every angle being measured from the same standard reference. Without it, every engineer would use different standards and give us different results on our work, and we won't want that. Now, you're in your second year and you're learning calculus and differential equations. Now you're adding the element of time. The angles are no longer fixed, they change, and the rate of that change matters. The perfect real-world example is the simple harmonic motion. In the real world, things move. The math that describes this change is called the differential equation. And look at the solution. It's our old friend cosine. But now the angle isn't just theta, it's omega t. The angle is now a function of time. Standard position is still the foundation, but now it's describing a system that is constantly in motion. In the Fourier transform, the angle in the standard positions become the engine of pure rotation to Euler's formula e to the power of I theta. The transform breaks down complex signal into a sum of these simple rotations. The angle, written as theta equals omega t, is what drives the rotation for each component frequency omega. A high frequency means the theta changes quickly. A low frequency means the theta changes slowly. The standard position angle is now the fundamental component that defines a signal's frequency. From standardizing the position of angles, we've created the prism that turns noise into layers of harmony that makes analyzing any type of signal possible. So basically, if you're confused about what I showed you, these are all the future topics and applications that you might encounter that take our angle substandard position and make it into its foundation or building block. Now, let me show you the culmination of all these concepts that stand out on the concept of the standard position, something you might encounter in third or fourth year of digital signal processing. This is the fast Fourier transform of a MIDI file in both the frequency and the time domain. I hope you enjoy it. Now that everything is wrapped on and widely learned this, let's actually go to the topic of angles and standard position, because that took a bit of a side trip for us to know its full potential. I will start with the terminologies first so we can get acquainted with the actual concept regarding this topic. Now let's start with the fundamental one, the angle itself. An angle is just a way for a ray to rotate away from another, with both sharing a common endpoint called the vertex. Every angle is formed by two rays, the initial side and the terminal side. The initial side is just the starting position of the ray before any rotation occurs, while the terminal side is just the position after the rotation. The amount of rotation between these two sides determines the measure of the angle. The measure of an angle tells us how much rotation has taken place from initial side to the terminal side. There are two main systems we use to describe this measure, degrees and radians. The degree measure is the more familiar one. It divides a complete revolution into 360 equal parts, called degrees. This choice traces back to ancient Babylonian astronomers, who used a base 60 number system and found 360 convenient because it matched roughly the number of days in a year and divided evenly by many numbers. So a right angle measures 90 degrees, a straight angle measures 180, and one pole rotation measures 360. However, in mathematics and science, another unit called the radian is often used because it relates angles directly to the geometry of a circle. To understand where radians came from, let's start with the circumference of a circle, which is given by the formula c equals 2 pi r. This formula tells us that if we move all the way around the circle, the distance we travel along its edge, the circumference, equals 2 pi times its radius. Now imagine a unit circle, which is a circle with radius r equals 1. If we measure along the circle's edge using the radius as our measuring stick, we can see how many times that radius length fits around the circle. After marking off one arc length equal to the radius, we trace one radian, an angle slightly smaller than 60 degrees. If we continue marking off equal arcs, we can fit around 6 full arc lengths before almost returning to the starting point. There's still a small remaining gap, roughly 0.283 of a radius, before closing the circle. Altogether, we can fit 6.283 radius length arcs around, and since 6.283 is just another way to write 2 pi, we can conclude that one full revolution equals 2 pi radians. This direct link between arc length and radius makes the radian a very natural way to measure angle. In fact, the definition of one radian can be written as radian measure equals arc length divided by radius. From this relationship, we can also find the conversion between degrees and radians, which is 180 degrees equal pi radians, or 360 degrees equal 2 pi radians. So to convert degrees, you can just multiply by pi divided by 180, and to convert radians to degrees, multiply by 180 divided by pi. Radians might look less familiar or less intuitive at first, but they are essential because they tie angle measurement directly to the circle motion, arc length, and periodic functions, ideas that become very important later in trigonometry and calculus. Now that we understood how angles are measured, we can define how they are positioned. An angle is said to be in standard position when its vertex is placed at the origin, which is 0, 0, of the coordinate plane, and its initial side lies along the positive x-axis. The terminal side shows where the rotation ends. This setup allows us to represent any angle consistently on the coordinate plane. When the terminal side rotates counterclockwise, the angle is considered positive. If it rotates clockwise, it is negative. For example, a rotation of positive 90 degrees counterclockwise is the same position as a rotation of negative 270 degrees clockwise. Both end at the same terminal side but have different direction of rotation. Angles can be also classified according to the quadrant where the terminal side lies. Quadrant 1 has the angles between 0 and 90 degrees. Quadrant 2 has the angles between 90 degrees and 180 degrees. Quadrant 3 has the angles between 180 degrees and 270 degrees. And Quadrant 4 has the angles between 270 and 360 degrees. If the terminal side falls exactly on one of these coordinate axes, the angle is called a quadrantal angle. Examples include 0 degrees, 90 degrees, 180 degrees, 270 degrees, and 360 degrees. Another important concept is of the coterminal angles. Angles that share the same terminal side, but differ by one or more full rotations. For instance, 45 degrees, 405 degrees, and negative 315 degrees all end up in the same position. In general, we can find all the coterminal angles using the formula theta coterminal is equal to theta plus or minus 360 n, or if you're using radians, theta plus minus 2 pi n, where n is any integer. Finally, there's the reference angle, which is the smallest positive angle formed between the terminal side of a given angle and the x-axis. Reference angles are always acute, meaning between 0 and 90 degrees, and they help us simplify problems involving angles in different quadrants by relating them back to the first quadrant. Understanding these definitions and relationships give us a complete picture on how angles behave in the coordinate plane. This knowledge sets the stage for deeper concepts later on, such as trigonometric function and their geometric interpretation, which all build upon the simple but powerful idea of an angle in standard position.